In this episode, now we can see about the seawater system, how seawater is used as a cooling media or heating media in offshore and Gulf region, and the marine growth prevention system used to protect the seawater. In offshore and Gulf region, once through seawater cooling system is used. Seawater pumps are used to supply seawater as cooling media or heating media. MGPS is in place to prevent marine growth within the system. Normally, at seawater intake in onshore or any seawater present in the Gulf region, bar screen, a mechanical filter is used to remove large objects, marine animals like turtles and big fish, rags and plastics in the open channel, followed by a rotary brand screen to remove further fine particles. Then it will go to the pump section. In offshore, seawater pump provided with a suction strainer and a discharge filter for being distributed for cooling or heating. The seawater temperature may be between 15 degree to 36 degrees centigrade. Either it is used in cooling media in heat exchanger or cooler, or as heating media in LNG regasification plant. In the LNG regasification plant offshore platform, seawater is used as a one-time heating media to regasify the LNG, which is at minus 163 degrees centigrade. So it is gasified by using the seawater only. The growth of sea life within the seawater system can lead to the destruction or shortened life of equipment and pipelines. To counteract this, the seawater system is protected against fouling by a marine growth prevention system. The system is designed to provide continuous protection against marine growth and corrosion caused by marine organisms in seawater pipelines, valves, and the heat exchanger. Also, due to the salinity of the seawater, it will give more corrosion to the seawater line. When in operation, the seawater from the seawater lift pump discharge via branch pipe to the electrolyzer module to produce sodium hypochlorite via the seawater inlet strainers and isolating valve into the degassing tank also for soft dosing arrangement. The activated seawater from the MGPS tank is discharged to an injector facility located at the seawater lift pump section, and the pump is started automatically. MGPS also will start, and the hypochlorite injection will be started to the pump section. Now we can see how the MGPS system is working. The MGPS produces sodium hypochlorite for dispersal to each of the seawater lift pump suction strainer by generation of sodium hypochlorite by the electrolysis of seawater. The electrolyzer cells control the sodium hypochlorite concentration production by increasing or decreasing the direct current applied to the electrolyzer cell. The transformer rectifier, which controls the direct current, is a current control design type having 10% to 100% direct current output, which is used in the electrolyzer cell to produce sodium hypochlorite. Cathode is used titanium, and anode is titanium and mixed metal oxide are used as electrolyzer cells. Each transformer rectifier output current supply is maintained at the desired set point value via 4 to 20 milliamps signal generator from the control panel to the electrolyzer cell. The electrolyzer cells are monitored and protected by the seawater flow continuously. A transmitter will activate the flow value, fall below preset low value, initiating an alarm, and if the level fall further to a low flow rate, it will activate an electrolyzer module trip. Since the direct current is going to the module, if there is no flow, that will affect the module and further flame explosion and fire. This will result in the standby electrolyzer module automatically operating when the trips the module with low flow. Also, if the low flow rate is increases to a bit, if the flow rate is increases to a predetermined high flow rate, alarm will be activated to reduce the flow to the module. The produced sodium hypochlorite is then discharged from the electrolyzer modules to a degassing tank. In the degassing tank, all the hydrogen is removed from the hypochlorite solution with a forced draft ventilation supply from two hydrogen distribution blowers operating in duty. One fan will be on duty and another will be on standby. Standby mode. The air from the blower is taken from the atmosphere and directed to the degassing tank via an inlet ducting and a vent to the atmosphere after removing the hydrogen. Also, the degassing tank is to provide a storage of sodium hypochlorite to provide shock dosing requirement. The shock dosing is carried out 3 times in a day for a duration of 20 minutes. Every 8 hours it is dosed. The system is set continuously to deliver sodium hypochlorite at the rate at a concentration 1.7 milligram per liter. Shock dosing can be employed to quickly raise the level in the system to 3 milligram per liter. This is the equation sodium chloride salt in the seawater. H2O. NaOCl is formed in the electrolyzer to the direct current passed in the electrolyzer cell and hydrogen gas also sir, which is getting removed in the degassing tank. A consequence of the electrolysis seawater is the production of calcium and magnesium and calcium carbonate within the electrolysis cells which form the hot scale. The unwanted product from the initially white, soft, fine particulate. The accumulation of these products on the surface cathode will reduce and eventually bridge the gap between the anode and cathode bipolar plates, creating overheating. The overheating will result in irreversible erosion of the anode's coating. To counteract the production of calcium and magnesium and calcium carbonate deposit, the use of an acid washing system to clean the electrolyte cell is used. So the MGPS production is reduced, and if you suspect or if you detect MGPS scale growth, then it should be taken for acid cleaning. Now we can see the acid cleaning frequency depends on the following for the MGPS system. It depends on seawater temperature, seawater salinity, the applied current load to the electrolyzer cell. The dual electrolyzer module design enables a module to be removed from duty to allow for acid washing without interrupting the seawater system sodium hypochlorite dosing process when the seawater pump is running. So one module will be in service and the other module if it is getting hot scale inside the module, then it will can be taken for acid cleaning. 7% HCl is normally used. 7% HCl cleaning solution is prepared within the acid cleaning tank using a service water or potable water. There is one conductive meter is provided in the line. We have to observe the conductive meter in the dosing line and concentration during the acid solution preparation. The concentrated acid will be diluted with potable water and we have to produce 1% HCl. And starting the filling, the solution is circulated to the tank and pass the conductive meter. The conductive value reaches 570 millisiemens per centimeter. Then the concentration will be roughly 1%. So it is concentrated and the required concentration for the cleaning of module to remove the scaling. Pump circulation should be started and 7% acid is ready for the acid circulation to the module selected for acid cleaning. Continue to circulate the acid until the conductivity meter remains stable and no further changes observed. So when you start the circulation, conductivity start increasing. So when it remains stable, stop the acid cleaning pump. The conductivity meter shows no further change in conductivity for minimum 30 minutes. If it is stable and conductivity is not rising, then we can stop the acid cleaning. Completely transfer the used acid back to the acid tank. Then we have to dilute the residual acid present in the module and drain it to the sewer. Keep the cleaned module ready for the next cycle for service in the MGPS system. Now we can see the seawater system outfall design limit. And the seawater system is used as a one-screw cooling media. It is to be let out in the outfall after the usage in the heat exchanger or cooler or in the heating media in the LNG regasification plant. Maximum FRC 0.1 ppm is allowed in the seawater outfall for being released to the sea and is discharged to the sea back after used in the system for cooling or heating. FRC should be 0.1 ppm. FRC in the seawater outfall will be monitored on a continuous basis by an online analyzer and to be confirmed by manual testing also. The maximum temperature is 3 degrees centigrade at 100 meter distance from the seawater discharge. That is, and the seawater inlet temperature is X means, and then the outlet temperature should be X plus 3 maximum, and it is discharged to the seawater. Minimum dissolved oxygen should be 2 ppm in the seawater before being released back to the sea. That is monitored continuously by an online analyzer. It should not affect the marine growth. And maximum hydrocarbon differential of 10 ppm is allowed in seawater before being released back to the sea. That is monitored continuously by an online analyzer. If any contamination of the hydrocarbon in the seawater cooler or heat exchanger, and the value should be less than 10 ppm, then only should be let out to the seawater outfall. Hope you might have understand the seawater system used in Gulf region and offshore, and the marine growth prevention system used to protect the seawater, and the seawater outfall design you have seen. Do not forget to subscribe and share it with your colleagues and friends. Put your like and comment in the comment box. See you in the next episode. Thank you very much.